and his works is on complex system applied to transportation models. So Luca, you have 12 minutes to present your work, and then we'll ask some questions. Go on.
Can you see my screen now? I suppose
we see your screen. I see your screen.
Then I record that, so I'll display.
Perfect.
Your questions. All right.
So we'll meet after for the questions.
Here's the outline of the talk. First, we're going to present the objective of the study, why we study buses. Then we will introduce an analytical theory of regular and express buses, where express buses is a new concept that we introduce in this work. We'll show some applications and limitation of this technique. And then in order to overcome this limitation, we will have a reinforcement learning approach to that can optimize waiting time in arbitrary settings. We will apply this to empirical cases and show the results that we are able to obtain. And in the end, we have the conclusion. So what's the object of this study? Buses naturally punch and are inefficient. This is shown in the literature. This is shown in the experience as well. You may have noticed that sometimes when you're waiting for a bus, you wait for a very long time, and all of a sudden you have 2 or 3 buses coming together, bunching. So this reduces inefficiency and increases waiting time. It's possible to have dynamic control to overcome this phenomenon, but they're very hard to implement in practice because that requires an active action from the driver and also a coordination in the system. So there needs to be a central agent checking the position of all the buses, the crowdedness of the bus stop. So in practice, it's hard to implement. So the problem we want to solve is, can we minimize the waiting time without the need for dynamical control? So can we just assign buses to bus stops in such a way that we can reduce the waiting time without introducing extra complexity in the system? So this is what this presentation is about. Here I'm going to present our analytical theory of regular and express buses. Here we present our analytical result for regular buses in terms of waiting time. Here we can compute the waiting time for a bus stop I, and then we can compute them in general. So, but what does it mean? So first, let's explain some working hypotheses that we used. Here people alight first and board after that. Then the destination of passengers can be arbitrary. Buses have the same natural period, the same velocity. And bus stops can be arbitrarily crowded. And we use this parameter Ki to measure how crowded they are. So Ki is proportional to the number of people arriving at a bus stop per unit time. Those are the results for express buses. Express buses are defined as having disjoint subsets of buses serving disjoint subsets of bus stops. So that means that in each bus stop, there can only be one subset of buses serving it. So there is no overlap. That's what simplifies the calculation and allow us to solve it for the waiting time. This seems a bit abstract, but we will see in an example later what it means. And so we can compute the average waiting time in a similar fashion as what we did in the previous case. So here is the case for the waiting time at a bus stop I, and here is the case for the waiting time in general in a system. As you can see, this depends on how crowded bus stops are and how many buses are in the subset and so on. Let's start with a simple case, a toy model where we have 2 bus stops, A and B, where passengers board buses and then they want to alight at bus stop C. This is a toy model, for example, can represent a morning commute scenario. And then there are 2 buses, X and Y. This is the first application. So what we mean by express buses. Regular buses, both X and Y would board passengers in A and B. But with express buses, bus stop X will serve bus stop A, so we'll pick up passengers in A, and bus Y will pick up passengers at bus stop B. So they split the loop into 2 parts in some sense. Here we can see performance-wise that by changing how crowded bus stop A and B are, how many passengers are there, we have different regimes. In this darker area, inside the red line, express buses have an advantage, have a reduction of waiting time that depends on those parameters. But in this region, in between the 2 red lines, express buses perform better. So if you look at the plot, you see that they tend to perform better when Ka and Kb are approximately the same. So when the two buses are splitting the job equally, almost equally. While in the scenario where one is much bigger than the other, then regular buses have better performance. But can we do even better? It turns out yes, but we'll need a new system to allow us to explore different configurations. Let's see another application in a more realistic case. This case has 6 buses and 12 bus stops. And here all the bus stops are different. So the number of passengers arriving at each bus stop is different. Those are taken from a paper that studied empirically data time series of buses in order to estimate how crowded each bus stop is. And we can see that we can have an optimal assignment because we have a theory of express buses, and we can see that bus 1 will serve bus stop IC, bus stop 2 will serve SPMS and LWN, and so on. So this is the optimal assignment given by the theory. So what is the advantage compared to regular buses? Turns out it's not amazing. The reduction in average waiting time is only 3.6%, but can we do even better? Yes, we can. With the system we are going to introduce in the next slides, we can reduce the average waiting time by 24% using reinforcement learning in our system. Here we introduce the reinforcement learning approach that we used. This is a tool for us to generalize our results for arbitrary buses serving arbitrary bus stops, because in the case of express buses, we are constrained by the fact that one bus stop can only be served by one subset of the buses, so there cannot be any overlap. We use Q-learning. Each bus at a bus stop can take one of the two actions: allow people to board, so basically serving that bus stop, or leaving the bus stop before people are allowed to board. Each bus bases its action only on the current bus stop. It's not based on any dynamic condition. It's not based on the distance between the bus and the current bus and the next one, or anything like that. That's why this is not a dynamically controlled. The goal of reinforcement learning is to minimize a cost. In this case, the average waiting time. Here's the learning rule, so how the system can actually learn. You can think about that as an agent-based model where each agent can learn based on the environment, based on the indirect interaction with all the other agents. Here we present how this system can be applied to the two cases that we've seen. First of all, let's apply that to our toy model, and here we can see an animation of what happens. But again, the system is passengers in A and B want to go to C. Turns out that there is a better solution than the express bus, at least in some regimes of crowdedness of A and B. We call this semi-express. So bus 1 boards passengers only from B, but bus 2 boards passengers from A and B. So in some sense, bus 1 is an express bus and bus 2 is a regular bus. So we call this configuration semi-express. This is unexpected, and we couldn't treat that in our theory because of the interaction that happens at bus stop B that is served by both buses. There is an analytical model by Vee-Liem, who is at CCS, so it's on Thursday 10, so I recommend you to check out his talk as well. And he shows that this system displays chaos. He uses maps to approximate these dynamics and calculate Lyapunov exponents, and he also has some exact results that unfortunately cannot be scaled up for more complicated system, but it's indeed interesting to see how chaos arises from such simple system. And how about the performance? Here we can see in blue that the average waiting time is very much reduced by the semi-express, even compared to the green, which is the express buses, and the regular buses in orange. This is true for a certain regime of Ka, so it's true for those kind of values. But of course, if Ka is too small or if Ka is too big, then it's not the optimal solution. So depending on the regime, we may have different configurations that are optimal. So let's see how this performs on our NTU bus loop, our empirical system that we studied, that we showed before. We have 6 buses, again, and 12 heterogeneous bus stops, each one with different level of crowd. This is very complicated. There are approximately 10 to the 17 possible configurations. So we explored that with our learning process. We tried 12 runs, and we checked the median and the best performance. So typically, we can reduce the average waiting time by 21%, but in our experiments, we were able to reduce it as much as 24% in the best case. So here we can have a sneak peek of how the training happens. So we have the training process here for example, bus 1. And we see that initially the the agent doesn't really know anything about the system, so it's very much random, and it slowly learns that there are some configurations that are the best. So here, for example, you can see that towards the end of the training, for example, the SPMS bus stop, this bus will stay. So it means that it will board passengers from this bus stop. And this, as you can see, is very complicated, and it's very, we couldn't treat that analytically because the interaction at each bus stop is very complicated. We tried this on a number of other scenarios, obtaining similarly good performance. So we are quite confident that this could be generalized for arbitrary bus loops with an arbitrary number of buses and bus stops. And here is the conclusion. So we set to study the problem of static assignment of buses to bus stop without dynamic control. We introduce express buses, and we can solve analytically for the average waiting time of express buses and regular buses. We see that express buses sometimes don't lead to very good performance, depending on the situation. So in order to address this complex interaction, we propose a reinforcement learning method that can generalize the exact method that we have. We discover an expected solution and chaotic behavior in our simple system. We applied a new technique to an empirically motivated peak hour scenario, very hard to solve, and we can see a reduction in average waiting time of up to 24%. So this again is with no dynamic control. So each bus knows where to pick up passengers and where not to pick up passengers. So thank you very much for your attention.
All right, thank you. So if you have questions, please you can share it, unmute yourself or write in the chat.
Yes, qui parle. Hello. Yes. So thank you. So it's time. Do you have any question? So Thierry's, everyone, it's there. So Thierry's, can you you can ask question either using the chat, or maybe you can be on mute. So is there any question?
I'd have a question.
Yes, go on.
First and foremost, thank you very much for an interesting talk. The question is, how, given your work, how could it be possible to change the bus stops to optimize the entire system further?
Oh, thanks for a question. That's an interesting problem that is not what we studied, but it's actually quite interesting. So by the analytical theory, actually, we are able to have some insights on how bus and waiting time works. So for example, one of the results that we got is by splitting a crowded bus stop into two separate bus stops, just one after the other, it turns out that with regular buses, again, buses that without any control, that they serve all the bus stops, with regular buses, the average waiting time actually increases in our analytical treatment and in our models. So this could be, maybe could partially answer your question. So maybe it's better to have more big hub bus stops instead of having a lot of them spread it out in terms of waiting time.
Thank you.
Hi, I have a question. Can you hear me?
Yes.
Yeah, so you're trying to optimize the waiting time. So are you considering also the carbon footprint, or how much emission is there? And do you have any idea to estimate what should be the fleet size, how many buses you need to deploy, depending on the bus stops, etc.?
So in this problem, we fix the number of buses operating the line in the loop, which is approximately true for normally, depending on the situation, but for a number of hours, it's normally true in our case that we explore.
And how do you come up with the number of the buses that you are deploying?
That is from empirical data that is measured in a paper that was cited. Let me see if I can find that. Anyway, we measure those data because we have GPS data where each bus is. So we know that at this time of the day, there are 6 buses. So we studied a few situations in which there are 6 buses in the loop. Normally, this is in the afternoon when students go from their classrooms, libraries, or whatnot to dinner, or they go back to their halls. and we observed that consistently there are either 6 or 7 buses. So we take some cases with 7 buses. We can estimate how crowded each bus stop is by estimating how long each bus stays in a bus stop. So it's explained better in that paper. Maybe I can type it in the chat later.
Yeah, sure. Okay, thank you.
Thank you. Other questions? Okay, so I will have a few questions. So first question, how can you use your results for real world situations?
So this is particularly interesting for applications because compared to other methods that have been used to reduce bunching and to improve performance, this is very, very simple to implement because bus 1, if you board bus 1, you already know that bus 1 is going to serve bus stop 1, 2, 4, and 7, for example. So it's fixed. The driver doesn't need to check an app, a signal to say, oh, should I wait? Should I serve this stop? So it's static. The bus driver already knows from the beginning that it's going to serve bus stop 1, 2, 4, and 7, for example. So this makes it very easy to implement. Other methods such as holding or no boarding requires some special infrastructure, for example, requires some special agreements with the passengers and so on. But here it's fixed, so it's static. And I think that's why it makes it easy to implement. Although, of course, with active control, performance can be improved even further. So, but that's
Other question, in fact, according to you, what are the main limitations of your method, advantages and the limitation of your proposition?
So the advantage again is that it's very simple compared to regular to other kind of control, such as holding the bus. So sometimes what buses do, maybe if there are 2 buses and the bus that is behind would stay and wait at the bus stop until the other bus pulls away. So this requires infrastructure, so it requires a place for the bus to park, to stay there, and it requires someone to communicate the driver, oh, now you wait a little bit until the other bus stops. So this doesn't have this limitation and this challenge. But at the same time, with active control, performances can be reduced even further. So now we were able to do, for example, minus 24% with a similar system with 3 buses. Again, 12 bus stops, but in a less busy period. For example, we were able to go down, I think, about 32%. So reducing waiting time by 1/3 just by assigning buses. But yeah, it could get even better, of course, if you let drivers coordinate and then decide on the spot adaptively whether to perform some action, whether to board passengers or not. But it's a different set of problems.
Okay, and the last question, how the problem become difficult if I had more and more buses and more bus stops? What are these type of limitations?
So this is an interesting question. In our paper, we explored different complexities of case. Here, I presented the simplest one and the most difficult one that has about, if you count them, about 10 to the 17 possible configurations. So it's really huge. Our system, reinforcement learning, is probabilistic. It's not an exact solution. It's not exactly the best. So you can run it for as long as you like. The more you run it, the better performance you get in general. So it's mostly limited by the computational power. But even such very complex system, if you run it like the 6 buses and 12 bus stops, if you run it for a relatively short amount of time, like 1 hour, half an hour, it can still reduce waiting time significantly by 10, 15%. Maybe it wouldn't reach the 20 and 25% that we see here by training for longer time, but it can still quickly improve from the baseline. Then the last few percent, as always, are the most difficult ones. But even such a system with a relatively short training can really show some significant improvement compared to the baseline, and even compared to using the analytical formula to assign buses, express buses based on that.
Okay, thank you, Luca. Thank you for your presentation. On peut pas applaudir, but it's okay. So now we'll go to the, yes, we'll go to the next presentation. I think it's, I saw him. It's Guoqiang Xu. Sorry if I don't pronounce your name very well.
Yeah, I'm Guoqiang. Yeah.
Okay.
You hear me?
Yes, we do hear
Yes.
you.
Okay.
So, are you a PhD student? Yes. And you work with Shlomo Havlin?
Yeah, I'm also I'm a joint PhD student. Now I'm back to China. Yeah.
Okay, that's right.
Okay.
So you are a joint PhD student with Shlomo Havlin and I don't know which university in China. And so you will present us the analysis and modeling of flight delays in air traffic system. Okay.
Yeah.
Can you
Okay.
share your screen? And
Okay.
please, people can answer questions while they are during the presentation, and please mute your mic. Thank you.
Thank you. So can you see the PPT?
Perfect. Perfect.
Okay. Hello. My name is Guoqiang Xu, and I'm a PhD student from Bnaya University and Beihang University. Today, I would like to present our study about the analysis and modeling of the flight delays in air traffic systems. So I will talk in these 4 parts. First is introduction, description, and some results, and final is the conclusion. So first of all, we'll introduce the development of the air traffic system. So the China has become the second largest market across the world in the recent years, and it has about 12% increase per year. But at the same time, the air transport system has reached the limits of airspace capacity gradually, which results in serious flight delays. And according to the Civil Aviation Administration of China, more than 20% of flights delayed every day in 2018. So what is a flight delay? It's defined as when an airline flight takes off or lands later than its scheduled time. And it can be described as the following basic process. So the first is the primary delay. The primary delay can be generated from various disturbances, including the extreme weather, the air traffic control, the airline issues, or aircraft malfunction. And also the primary delay can be transferred and amplified by the aircraft flight routes. For example, the flight delay from CTO to PK can be transferred to its connecting flight from PK to Shanghai, SHA. So this is the basic process of the delay propagation. And the next is the data description. Our analysis are based on 2 data sets. The first is from China. We collect from the Virgin website. This database concludes 5 data months, 5 months data. It concludes the airport information and also the information for each flight. We can calculate the departure delay from the scheduled departure time and its actual departure time, and also it has the departure airport weather. It can allow us to analyze the correlation of the weather and the flight delay. The second is the America flight information we download from the BTS website. And this is includes 1 year data in 2019. And it also has the schedule and the actual departure delay. We can calculate the departure delay. And also it has a special tail number. The tail number, we also called it as the aircraft identification code. So we can contrast the flight routes with this information. So the next is our results. So first, we analyzed the PDF of the flight delay, departure, and arrival delay for both China and the US. So while the earlier studies suggest that the normal distribution, but we found this is better fitted by the log normal distribution, both in China and America. And the right column is the comparing of different fitting functions about the log normal, the power law, the exponential, and the normal. It's been clear that the log normal is the best fitting. So why it can be a log normal distribution? First, we show the correlation of the delay and the factors of the relation factors about the delay, the primary delay. The first is number of flights. So it's obvious that the more flights will produce more delays. So it shows a correlation between China and US. The US has a stronger correlation than China. This is the traffic, and also is correlated with the airport weather condition. So for the weather information in China, we first group it to eight groups, from 1 to 8, from the good weather to the severe weather, and it shows that the bad weather contrasts to more flight delays. So if we comparing the delay distribution of two best and the two worst groups of weather, it shows an obvious difference. So especially for the primary delay, we also analyze the delay propagation. Also, it's memory. It's memory between the consecutive flights. So we analyze the flight delay by following the flight routes of a specific aircraft, and cut the flight routes. We cut flight routes with peak hour. So peak hour is a aircraft stay time in an airport. So if it stay at the airport more than 5 hours, we cut it. We get route 1 and route 2. So in the following, we analyze the departure delay and arrival delay in the same flights, the correlation, and also the arrival delay and departure delay in 2 consecutive flights. So this is the scatter plots and the conditional plots, conditional PDF plots. So for the conditional PDF, we first sort all departure delays in ascending order and divide them into 3 equal quantiles. The green area is the conditional PDF of the first quantile, and the purple is the third quantile. If the overlap is small, it shows a strong memory. So both we can see from the scatter plot and the conditional PDF, we can see we can see that it's had a strong memory between both the departure and arrival delay in same flights, and the arrival delay and the departure delay in consecutive steps. And also we analyzed the the departure delay in one step and departure delay in another step in the following step. So this memory allow us to strengthen the assumption of the multiple process in the following. So based on the this flight delay memory, we can construct this modeling to simulate the flight delay. So for specific flight routes, the delay in the T step and the delay in the T+1 step, we multi it by a small factor, and this we call it a flight delay memory. So if we multiply by many steps, the factors will be the log normal, the multiple process will be, when we take log process, it will be a assumption of many small variables. So the log will be normally distributed, and the original T step will be log normal distributed. And this is our modeling. So we do the simulation in the next. We first, so we construct 100 flight routes with the multiplicative in simulation. And the initial delay of each route is randomly chosen from the real data. And the change factor of the next delay are generated according to the conditional PDF of the successive departure delay we analyzed before. And this process is it can reproduce the distribution of flight delays. So this is our simulation results. So we take different steps and we compare the simulation and the real data. It can be seen that for 4 or 5 steps is very similar, and it is fitting very well between the real and the simulation. And we also do more steps, but not so good. And why so is 4 or 5 steps, and we can also see this from the real data. For the real data, if we after we cut the route, we can count the route length, and the length is concentrated on the 4 or 5 steps, and is same with our simulation. So this are our results, and this is the summary of our study. And so first, our study suggests that a low normal distribution is more fitted, is more better for the delay distribution, and we find a strong memory between the successive departure delays. And this memory indicates the multiplicative process, and our simulation is well fitted with the real data. Okay, thank you for listening. Thank you. That's all.
Okay, thank you for your talk. So, any question? Is there no? Okay, so I have one first question. My first question is, you said that historically people were using a normal distribution, and you propose to use a log normal. And it seems to me a little bit strange because, because the log normal is disymmetric, normal is symmetric. So how did people end up with a normal distribution?
Okay,
yes,
Yes. The normal concludes negative values, but the log normal is only for the positive values. And the earlier study is just a normal distribution for the departure delay for all the negative and positive values, and we only consider the positive values, and we fit it by the log normal.
Okay. Okay.
And we can, from this comparison, for the positive values, it also shows that the log normal is well fitted, not the normal, like this line.
Okay. We have a question from Naoki Masuda. Go on, Naoki.
Sure. Thanks for great talk. So my question is regarding regards the differences between the US and China. So I understand that your model and explanation using log normal and say the delay, the correlation applies to both the countries. But at the same time, you show some differences in the two countries, like in slide 12, which you're showing. The US has a stronger correlation. So do you know why, why two different countries are different in some aspects?
So the America shows a stronger correlation. I think for the China, it's maybe because the some regulation for the I think it's more correlated by the delay propagation, not for the primary, because the number of flights I think is only correlated with the primary delay and not the delay propagation process. And also the America has some long routes from Hawaii to America to mainland, and for China it's more concentrated in the east and the north of China.
I see. Yeah, that's interesting. Thank you very much.
Okay.
Okay, thank you.
Other questions? So I still have another question, and it's related to the question, I would say, of Naoki, because in your model, there is no relation with the infrastructure, I would say the network, at no moment you are taking, you look at the network of the route networks, no? Do you?
For now, we don't consider the network structure. We just construct the flight route of each aircraft.
Yes, you're working on aircraft. Okay, but maybe the explanation of the differences lie on the network topology. No, what do you think about that?
I think, yeah, maybe it's also about the network structure for maybe the correlation of the airport capacity, maybe. So for now, we only take the multiplicative process from the analysis of the flight delay memory. We construct this model. Maybe later we can construct a more realistic model for the consider with the network structure and also the capacity of the airports. Construct a more realistic model.
Okay, I have another question, more general, I would say. How can we use your results to improve the effectiveness of the traffic? Do you have any idea?
To improve the...
Yes. So you have been studying the delays, but when I know things about the delays, how can I try to improve the delays?
Try to improve the delays.
Yes, to be more efficient.
To be more. So for now, it's just understanding of the characterization of the flight delay. But for my opinion, if we can make the air traffic system more efficient, maybe we can make the buffer time at the airport larger, so it will be not it will be show a less correlation between this flight delay. So because if we set a buffer time more buffer time at this airport, so the correlation between A to B and B to C will be less, and the delay propagation will be not so efficient, and the delay will be decreased. In this, I think.
Thank you. I have a last question. It's, I've seen a few works about, propagation of delays using SIR model. Do you know this kind of works and how it relates to your work?
SIR,
Yes.
SIS?
Yes, SIS or SIS model, yes, I think.
Yeah.
Because it's a propagation process.
Yeah, it's like the epidemic process. Yeah.
An epidemic process, because when you have a delay in an airport, after that it propagates through the. So, and they are using the network structure to propagate the delays between airports.
Yeah, okay. It's between the airports, between the progression from one airport to another. But our model is based on the flight route for each aircraft.
Yes. Okay, yes, it's quite different. Okay. Okay, thank you. Thanks a lot. Thanks.
Thank you.
So now we go to the next presentation. So next presentation is thanks from Juste, I think. Juste Raimbault. I think that Juste Raimbault. Are you French?
Yeah, yes. I'm French.
Yeah, so he's French. That's why. So it's Juste Raimbault. So he's a geographer working at UCL right now. He has been working also on Paris, and he worked on agent-based models of urban systems. Voilà. And he will present us, it's a very long title, a coevolution agent-based model for system of cities and transportation networks with governance included. Go on, using game theory. Go on, Juste.
Thank you very much for the kind introduction. And sorry for the very long title, but since this model is an extension of a first model, and which was already an extension of a first model, it's like adding the title and the title. But yeah, I prefer to be. And I just would like to thank, before beginning, Elsa Cote and Mike Batty, because this project actually began in one courses on urban simulation that they gave. And I had to design some model for the students, and it ended in this project. So. Okay, let me just put the context a bit, the thematic context of this. We all know that accessibility is quite important in the interaction between transportation network and infrastructure networks and the territories and the evolution of territories. And so this is an example taken for this chapter I wrote on China of the accessibility impacts of, for example, the Hong Kong-Macau bridge. And on the right is the accessibility impact of public transportation development in the last years in the Chinese cities. And with this very fast accessibility changing, we can expect also fast relocation of economic activities and households, and so fast evolution of land use. Then a bit more on the theoretical framework in which I work. So it's the Evolutionary Inventory, which was proposed by Denis Pumin more than 20 years ago, actually back in '97. And this book was the result of the geodiversity ERC by Denis Pumin. So this theory looks at cities as complex systems and evolutive complex systems. And there are three main axes. First, building styles fact and harmonized databases for system of cities. Then constructing simulation model for system of cities, and these are explicative models. So trying to understand the processes and so on. And then also building tools and methods to explore and validate a simulation method. And this is in particular the open model platform, which integrate new methods to validate simulation models. So, and a bit more particularly on the why coevolution. So this is from my thesis. We know that beyond just the interactions between cities and transportation network, we can assume that we have a coevolution between the two. So at one time step, so the cities will influence network growth, and then network activity will influence the cities' growth rate. And this is a model of coevolution, a simple model of coevolution, which was introduced in this chapter. But yeah, just to say that it remains quite simple, and the network growth is just updating the distance depending on the flow. So it's very simple, and you don't have any agents taking any decision for the transportation system. So how did I come to the subject I present now? Is that in a lot of contexts, you have some international decision on transportation infrastructure projects. So this is a few examples from these papers. For example, the Denmark-Sweden bridge. So I think it's Øresund Bridge. The Hong Kong-Macau bridge. So it's not really multinational, but kind of. The Channel Tunnel also is a multinational investment. And here it's the Lyon-Turin railway tunnel also, which is a multinational investment. So this infrastructure project significantly changes accessibility landscape in both countries, and are pushed by both governments. So in most of projects, you have a collaboration of the two governance part. Okay, I will go quite quickly on the literature on multinational transport investment. But we know it was shown by economic literature that there is a positive effect of transportation investment in this meta-analysis, for example. And also, for example, if you look at the One Belt, One Road infrastructure project, you've got already some positive impacts in terms of GDP, for example. But it is also known that these kind of multinational projects are difficult to implement. And also that, for example, the Trans-European project, like all the corridors and this kind of stuff, actually fail when you try to do the cost-benefit analysis. So the question is is it good to encourage this, and how to do this? And for example, you have some framework proposed to prioritize these infrastructures. Then going a bit closer to the model, how to integrate governance process into a coevolution model. So how to make the coevolution model more complex. So David Levinson with Xi is a kind of a reference in the network growth literature, transportation network growth literature, and they proposed already a long time ago some model of governance choices to grow the transportation networks. And it also specialized in a simulation model, so more simple on the theoretical side, but with a specialized aspect. And more recently, we proposed the land use transport interaction model with Havlin and Esche, with evolutionary network and game theory for actors. So it's at the scale of an urban area and game theory to include the decision of actor constructing the transportation network. And then just to mention that game theory is quite used in transportation literature, and a lot of transportation models and transportation economic use game theory models, like for example, competition between high-speed rail and airplanes, public-private partnerships, or the integration of public transport. So what do I try to do here? What is the proposed approach? So it is really to include both bottom-up and top-down planning processes in the coevolution, and to try to have some stylized but still applicable models for these governance processes. So the idea is to explore this coevolution model at the macroscopic scale, and focusing on trying to introduce rules for the network evolution, which include governance choices. So what is the rationale for the simulation model? So we extend, I think maybe that, okay, the reference should be fine. We extend the first model, which was the chapter already mentioned. So the very simple coevolution model, which was already extended with a physical transportation network in its other chapter. And here we include 2 governance levels for the decision of improving infrastructure. And for this, we use the game theoretic module cooperation, which was introduced actually by the work I already mentioned with Florent. So it's still quite simple in the structure. You've got cities described by population and a physical network with links, and each link has an effective distance with kind of an impedance. And it's a kind of macro scale Luti model in an iterative way. So at each step, you will update the spatial interaction flow, then you will evolve the city population depending on these flows, and then you will evolve the network speed and you iterate like this. Okay, just to give a few questions, but I can go quickly on this. It's really classical spatial interaction flows with one single parameter for both population. And we assume that growth rate of cities are proportional to the sum of flows going into these cities. And there is a parameter to modulate the share of international and national flows. So it's an exogenous parameter. You can see if a country exchange a lot or not, how does it influence model outcomes. Then for the network, it's based on a self-reinforcement function. So this was a function for the already simple model. You assume that link speed will self-reinforce according to if the flow is higher than a threshold. So this threshold phi 0. And to fix it, you have a parameter, phi0q, which is a quantile. And you say that it grows only if it's higher, otherwise it does not decrease. And you've got a hierarchy parameter, so saying does a faster link grow faster. So, and then from this value of possible improvements, you will estimate for each country, so we have 2 countries in the simplified setting, the accessibility gains of either implementing an international infrastructure, so ZDI here, or implementing a national infrastructure. So national and international, and you can also estimate the cost. And from this, you will then compute the collaboration probabilities. I will detail it in the next slide. So we assume a game theory framework, and we have this utility metric for 2-actor games. So for collaborating, saying, okay, we do the international thing or we do the national thing, and non-collaborating, and you've got this cost, which are the accessibility gains minus the construction cost, and you've got a collaboration cost parameter. So you've got all the international only if the 2 cooperate. Otherwise, you lose the collaboration cost if you wanted to collaborate, but the other doesn't want. And you have still the same utility function, but with the national infrastructure. Okay, you can solve the general Nash equilibrium with this probability. And this gives this expression for the probability of one country wanted to cooperate with the other country to build the international infrastructure. Okay, there's just a bit of kitchen work to fix the parameter values, kappa, so the cost to accessibility ratio and the collaboration cost given like effective interpretable parameters. So we run a baseline model, and from the average values of the baseline model, then we rescale the parameters. So it's because otherwise the value depends on the spatial configuration and arbitrary scale of the values. Okay, we go on with, so it's implemented in NetLogo because for such a model, it's good to have interactivity, but it's remains fast. We apply it only on a synthetic system of cities for now, and we integrate it into the OpenMODE platform. So we do some numerical experiment, including global sensitivity analysis, studying the role of stochasticity in the model, and some grid experiments. Just to mention, you can OpenMODE is open source software and free, and you can go download it and collaborate also if you want. So this is an example from the same spatial configuration. But on the top, it's a baseline model with no international national things. It just as it were one country. And you see that these links have, in the end, have ended up being the most reinforced. And the bottom, it's a mix of a national and international investment. And since each country, so the boundary is in the middle, is the green thing. since each country wanted to invest for some time in their own countries, you see that the international link is smaller. So it's basically the outcome you get. Okay, I didn't mention the indicators. There are a lot of these, but for now we just look at the average population growth, the same for accessibility. So did we have a relative good gain in accessibility? Also the change in population hierarchy, the population rank correlation is quite interesting. So did you have a lot of, was there a lot of changes in population dynamics? Then also the effective governance level and the total cost of the constructed network. So this is a result of the global sensitivity analysis. So it's this matrix of, as a function of parameters, the effect of either of first order or total order on the indicators. I cannot detail everything, but we see, for example, an effect of the spatial configuration, looking at the random seed and also the hierarchy parameter. So this is quite important. And we also see a cross effect between, so like network parameter affecting cities parameter and the overlay around. And also, of course, for the governance parameter, K0 and P0, the stronger effect is on the governance level, but you still have effect on the other indicators, although they are smaller. Okay, just to validate a bit internally the model, you need to look if the random noise is too much for you to draw a conclusion from it. So we did 100 parameters sampling with latent hypercurrent sampling, and for each we did 100 replication. So since the model takes like 1 minute and a half to run, it's already a lot of simulations. So we find quite a high value for the Sharpe ratio, so average divided by standard deviation, so it's good. So it means that noise can be neglected in most cases. So you see the first quartile is at higher than 7, so it's large. And also if you look at the distance between averages relative to the standard deviation, you also have a high value, so it's also fine. So this example of histogram, you see that you can differentiate taking the mean of the distributions. You are able to differentiate between the indicators, and it's not just everything noise. Then the result of the grid exploration. So on the left is, for example, the relative gain in accessibility as a function of gravity decay. And so we see that relatively, if we have a larger span of spatial interaction, so higher value of gravity decay, we'll have a smaller, so it is this decrease, smaller relative accessibility gain. But less hierarchical flow, so it's in column, the parameter gamma, will also decrease the relative gain. So having flows between larger cities is better for accessibility. And here there is not really much significant difference of the governance probability on accessibility. Just in this case, you've got a small for small values, but it needs still to be validated statistically and so on. Then if you look at the other indicator, for example, the governance collaboration parameter, effective governance, you of course have a strong effect of the governance parameter, the P0. And you see that the effect of interaction decay on this governance collaboration will qualitatively change when you increase the P0. So at the beginning, it was decreasing and plateauing, and for other values, so it's more noisy, but still you see that it increases. So there is this inversion, qualitative inversion. So we've got this nonlinear effect in the model. And finally, if you want to try to optimize both accessibility and cost of the network, so it didn't have time to do some calibration experiment and trying to obtain the Pareto front. So it's a result from LHS sampling. But still, so we want both to maximize, and it's a condition to a hierarchy and the C0, so the international parameter. So for high values, so the column on the right of international exchanges, we see that if you look at the Pareto front, so the point on the top here and here, it corresponds more to intermediate values of collaboration. So the higher are inside the cloud points, and also the lower value of collaboration are inside the cloud point for this point. So it may mean that, so it still also need to be confirmed with a specific calibration algorithm and so on, but that intermediate values of collaboration are better for the compromise between accessibility and cost in a global, in international collaboration. So just to discuss and conclude, there are a lot of development still to be done to this, and it actually goes toward already a macroscopic land use transport model, which are not that much explored. For example, there is a quant model at CASA developed, which is this kind of model, but it's still a lot of to be investigated. Then we could also, discussing with economists, we could do a lot in the decision-making modeling and governance process. And it's very simple for now, but still it's already a complicated model. And then also maybe try to integrate this into multi-scale models, as the one I presented last year at CCS. How can you apply this to real system? You could imagine to evaluate transportation projects in multinational stakeholder context. So, but when applying this to real system, and also maybe applying this to sustainable planning on long-term scale, because you include the coevolution and you include the behavior of agents and so on. Okay, just to conclude, I described a complexification of the coevolution model, including social governance. And one assumption behind this is that we have a standardized model which are well understood and explored, can be a first step toward policy applications. So everything is on GitHub, both for the model and the results, and you can also get the simulation dataverse here. Thank you very much. So you can take any question at this time.
Thank you. So any question?
I have one. So how do you quantify accessibility?
Yes, sorry, I didn't put the formula. It's a generalized accessibility. No, I don't have it. I didn't have time to put it. I reserve slide. Accessibility is a generalized accessibility. So it will be the sum of your population and weighted by the interaction flow. So it's how much population your population can reach. And you define this for each city, and then you will take the average.
So is it on certain time scale? Because given enough time, the population can definitely reach all the places. So is it on a particular time scale?
Of course, yeah. It's you got this decay parameter. Let me go back to the equations. Actually, it's close to this. You've got this decay parameter dg, which is exactly the span d0. Sorry, here, which is exactly the span of the accessible population. So, and your accessibility depends on this parameter, of course.
Okay.
So it's within a certain spatial interaction time frame. And then, sorry, you also made me think of something I didn't mention, is that we simulate the model for a fixed number of time steps, and it's 30 time steps, so it's around 1 century or 50 years. So it's because also if you iterate the model to infinity, then your population goes to infinity, accessibility goes to infinity, and so on. So it doesn't make any sense.
Okay, thank you. I'm not sure if we still have time. I think that no, I don't think that we have more time for that. So I will thank everybody, and I want to remind you that tomorrow there is a satellite on urban complex systems, which will last 2 days. So from tomorrow, Wednesday and Thursday afternoon. So I invite you to join the satellite. Okay, so thanks a lot, and see you in the next session. Bye-bye.
Bye.